Hello. So, in this video, we're going to be introducing the idea of closeness in a rigorous sense. So, in previous video, we talked about sort of the underpinning of these limits ideas from a geometric idea, trying to build sort of intuition. And in this one, we're going to be trying to tackle what we mean when we say suitably close or arbitrarily close or close enough, these sort of vague phrases that we've used a couple times before. So in general, most of what we consider as calculus, the idea of like finding shapes and filling things and finding instantaneous velocities, a lot of these things that will come up and we'll talk about at great length, a lot of this stuff was actually sort of figured out by people long before Leibniz and Newton and such, when we were the people we sort of say invented calculus. By way of example, one such method was actually done by the ancient Greeks, and they did a lot of different things actually, but the thing that we're going to use as an example is calculating pi, right? So they wanted to understand this idea of the ratio between the diameter and the perimeter of a circle, what we call pi. And to do that, they didn't have the tools that we have, so they were trying to figure out a way to approximate what that would be. And they did it by what they called the method of exhaustion. So they started with the circle, and then they would fill it with a shape. So for example, they would fill it with a square. And they would say, okay, we can figure out the perimeter of a square. This is a nice regular polygon. And they would figure out the perimeter of the square and say, okay, that's sort of close to what the perimeter of the circle is, but not that close, right? So for example, we have all of this like negative space between the circle and the square. And of course they realized this. So what they did next is they say, okay, we have this approximation. It's maybe not that great, but instead of using a square, what happens when we use a pentagon, right? A five-sided shape. So they would calculate the perimeter of the five-sided shape, and they note that there's less of this negative space between the circle and the pentagon, and so it's a better approximation. And then they would repeat this process with a six-sided shape, right? Even less of that negative space, better approximation. Then a seven-sided shape, then an eight-sided shape, and then 9 and 10-sided shape, right? And they would just keep going, and exactly this process is why it was called the method of exhaustion. They would go until they got tired and then be like, all right, that's close enough. That's basically our approximation for what the value of pi, this ratio, is. So doing this process, ancient Greeks, around 500 BCE, they got to an approximation of 3.14, which, considering the way they're going about this, is actually pretty good. This was still the sort of best method that they had, mathematicians had, for the next 2 millennia. So over the course of 2,000 years doing it this way, mathematicians sort of got better and better approximations. And notably, one mathematician spent literally 20 years of his life doing just this, doing bigger and bigger shapes, more and more sides. And he went up to 2 to the 62nd power number of sides to the shape inside the circle to get this approximation. And he managed to approximate 32 digits of pi over the span of 20 years of just doing these calculations. So in come the inventors of calculus, as we say, Newton and Leibniz. So these guys supposedly invent calculus. We say this, but really what they did is they invented a rigorous way, a very sort of analytic, algebraic way of dealing with this process of iterating things sort of to an infinite level, getting infinitely close to the right number, or getting an infinitely large number of sides to these polygons. And using this technique, using this actual rigorous concept of limits, within a few weeks, mathematicians could do 100 digits of pi. So we have the method of exhaustion, doing it step by step. That was, got you 32 digits after 20 years of calculations, versus a few weeks using this idea of limits to get 100 digits. Okay, so this sort of underpins the sort of shows the power of what limits can achieve, this sort of very rigorous idea. But sort of getting back to the beginning, we wanted to understand this idea of being close enough, right, in some rigorous sense. But inherently, this is going to be very difficult because what it means to be close enough is sort of inherently abstract to the concept, onto the context, right? What the context that we're talking about is what determines being close enough. So for example, a galaxy, right? If you want to know how far away a star is or how far away a galaxy is from us, a nearest mile would be incredibly accurate. It's much more accurate than we can actually do right now. But the nearest mile, maybe not so great for measuring the height of somebody, right? Like, that's not going to work so well. Everybody would be 0 miles tall. That's not helpful. So maybe we say, okay, nearest inch, right? That might be more intuitively satisfying. An inch we think of as a small unit of measure as opposed to a mile, right? If I say a mile is close, you're like, that seems sort of off, intuitively. But even something like an inch, when we talk about, atoms in a particle accelerator, trying to hit one atom with another atom going, appreciable fraction the speed of light, and a nearest inch is nowhere near close enough, right? So what we sort of want as close enough is very context driven. So in particular, context determines how close something needs to be. And our whole sort of goal in mathematics is to be able to create a system that works for everybody. It's sort of context neutral, right? So if we're going to come up with some system that can simultaneously give us information that is close enough, but not know the context, this is sort of a very difficult thing to be able to do. This is why it took so long for someone to figure out a way to get this to work. Hence, Newton and Leibniz. So what they actually did is they introduced this idea of arbitrary closeness. So for arbitrary closeness, if we say something is arbitrarily close, the whole idea of being arbitrarily close is that we are assigning some sort of distance away. We say that a point is arbitrarily close if it is within some unit of distance that we leave as a abstract variable. So we typically denote this distance as an epsilon, little e bit, which if I can get this to point right, so that's your epsilon there, or delta, that little sort of weird curvy d. These are Greek letters. So we would say that it is arbitrarily close because it is, epsilon distance away for whatever epsilon is. It's this sort of unknown variable or letter, what we would call an arbitrary constant, which is not an accident. This arbitrary is used in the same way in both cases. But the whole idea is that then we do all of our sort of computations and things using epsilons and deltas so that when somebody comes along and they say, okay, my idea of closeness is within a mile, that's what we would plug in for epsilon, right? And then this epsilon can be any of those things. So within a mile, right, doing galaxies, that's what epsilon is. Within an inch, right, you're doing height, that's what you plug in for epsilon. Within a nanometer or something, that's what you would plug in for epsilon. So we leave the context sort of able to be plugged in after the fact. Now, as a note, in this particular class, we're not going to be getting sort of super deep into the actual epsilon delta arguments themselves, like exactly how that works. There are optional videos if you're interested, so you can see how that works. For our sake, though, what we're going to be doing is more of a intuitive understanding, but it's important to understand the idea of what it means to be arbitrarily close, because this is going to come up again and again and again in this class. So that's the part you want to take away is this arbitrarily close. What we mean when we say that is that this is something that we're leaving unknown to be plugged in later. So it's a constant for the sake of any calculations we do, but it is unknown, so we can't replace it with a number like 5 or something like that, okay? So this sort of wrap up what we've talked about. Getting close enough is sort of inherently a matter of perspective. Understanding what it means to be close depends on what the context is. But that means that we can never actually sort of definitively choose a point that is close enough, right? If we decide, okay, a point that is 1 inch away is accurate enough, then we don't get particle accelerators, right? So we need some way of sort of rectifying this problem of it depends on context, but we don't have the context when we're doing the math that underpins all of this. And this is where we come up with the idea of being arbitrarily close. So we use this idea of arbitrary closeness to be close enough without knowing what the context is. Essentially, we're using this sort of unknown variable so that we can plug it in after the fact and have all the computations go through by just substituting it in once we know what that context is later. Okay, so that is that.